Hi guys, welcome back. And 9.3c, we're going to finish up hypothesis test for means. We're looking at paired data this time. So we're paired data, mean difference. So again, when you're doing the hypothesis test for paired data, just like we did the confidence interval for paired data, once we pair stuff, we treat it like it's just one sample. All right, so that's the t-test is the test that you would do for one sample. All right, so again, we state what mean difference stands for. It'd be the true mean difference between two things. Our null hypothesis is generally that the difference is 0. It could be equal to a number. That's also possible. An alternative would be that it's like greater than 0 or not equal to 0. You could also say less than 0, but as long as you like switch your list around, you could always do it so it's greater than 0 or not equal to 0. So like if one list you can see it's going to have a bigger average than the other list, or what the numbers from one set seem to be bigger than the numbers from other set, we can always set it up so like L1 minus L2 or L2 minus L1 is greater than 0. All right. The name of the test is paired t-test for mean difference. So it's not one sample or two sample, it's paired. So it kind of is one sample. It could be considered two sample. So since we're not entirely sure which one it is, we just say it's paired. All right, we need either a random sample or a randomized experiment. So this could be, flipping a coin to see who does treatment A and who does treatment B. Our randomization there takes care of that. The normal sampling distribution for mean stuff still applies. So we either need a normal population or a sample size greater than 30, or we need to look at the graph. Most of the time here, it will be the graph. So make sure you can do those graphs. And independence, we should be less than 10% of the population. All right, so we're doing the t-test on the calculator because we're treating the one sample as like that third list, L3, the difference between the first two lists. Write down all the stuff. It's like the sample mean difference, like X bar difference, the standard deviation of the difference, the N for the difference, how many things are in your sample. If you have degrees of freedom, write that down, your p-value, your t-value, all those things write down. All right, and then if p is low, reject the hoe. If p is greater than or equal to alpha, fail to reject, and then write another sentence about the alternative hypothesis, which includes context. Here's our example. All right, so researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from any substances with caffeine for the duration of the experiment. Over 1 2-day period, subjects took pills containing their normal caffeine intake. During another 2-day period, they took placebo pills. The order in which subjects took caffeine and placebo was randomized. At the end of each 2-day period, the test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. The table shows the subjects' depression scores. Higher scores show more depression. Do the data provide convincing evidence at the 5% significance level that caffeine withdrawal increases depression score on average for subjects in the experiment? All right, so there's not a ton of room here, but looks like we've got one subject doing two things. All right, so since that subject is doing two things, that's what tells us that this is paired. All right, so that means we are looking at the mean difference between the two. All right, so that's what's letting us know that it is paired. It's one subject doing two things here. Definitely going to be paired data. All right, so to actually work this out, let's see. Make my box here. So the mean difference then, I think I left an eye out. There we go. Is the true mean difference in, let's see, we're talking about depression scores. For caffeine minus placebo. All right. Our null hypothesis is that the mean difference, that the caffeine will make no difference. Our alternative hypothesis is that there is a difference. So that's going to be greater than 0. All right? Higher scores, right? Look, we're looking for, let's see, increase. There we go. So we think there will be an increase. And I actually probably want to do this the other way around, actually, because the placebo numbers look higher, right? The placebo numbers are higher, placebo higher, placebo higher. So it'd be placebo minus the caffeine. All right, so usually I got to look at that first, but it doesn't matter. If we did it the other way around, we could just say less than 0. It would work just fine. Our alpha here is 0.05. Our sample size is 11. We don't know anything about the sample mean difference or the sample standard deviation difference or any of that stuff. All right, but we do know that this is a paired t-test for mean difference. All right, we don't have a random sample like we had volunteers, right? But we randomized the order. So somewhere in here, I underlined on the last slide, there it is, randomized. So we have a randomized experiment. So that adds that element of randomness that we need for an unbiased estimator. All right, our sample size is 11. So we need to look at the graph. All right, so I'll come back to that. And lastly, for the independence, n equals 11 is definitely less than 10% of all. And these were what, caffeine addicts, volunteered with caffeine dependent people. I bet we probably have more than 11 of those in class. So as long as there's more than 110 of them on Earth, we should be okay. So now we need to look at the graph, and we need to put these two guys in lists. So let's take a look at the calculator. Here's my calculator, and I've already got them in here somewhere. Excuse me. All right, so L1 looks like our caffeine. Yep, there's our caffeine, and my 11's right. That was what was messed up in the last video, is the 11 was in as a 1. And here's the placebo, and the placebo is bigger. So for L3, I want to do L2 minus L1. So second L2 minus second L1, enter. There's our list. So that's the list that we're going to do our test with. And that's also the list that we want to look at the graph for. So second stat plot. And really, we just want L3 on for the box and whisker plot. So second 3. And I need to turn off my other stat plot here too while I'm at it. Should be quick, off. And zoom 9 to see the graph. And there's our box and whisker plot. So a little bit wider on this end, but nothing major going on there. So we got a little bit, and we've got a box. Line was about in the middle, and then it was a little bit longer on this side, but there's no outliers, right? Because outliers show up as points, and it's not strongly skewed. All right, so we're good there. So that means we have an approximately normal sampling distribution. Check. All right, we're going to do a t-test because really we're working with one sample and we're using data, and our data is in L3, or at least mine is. If you want to put those data in your calculator, just pause it, put it in. All right, so stat, test, t-test, there it is. All right, we're using data. All right, the mean that we are looking at is 0. We want to know, is it greater than 0? And our list was L3. So second 3, frequency 1, greater than 0, greater than the null hypothesis, so greater than 0, and calculate. So T is 3.53 and P is 0.0027. So the T is 3.5 and the P value is 0.0027. All right. So that's pretty low. Looks like we're going to end up rejecting. Our X bar is 7.36. So X bar difference is 7.36. And our standard deviation for that difference is 6.9. All right. So we put down all of our important statistics here from the data. And this is what we got out of our test. The T is 3.5. That's pretty far away from 0. And our p-value is very, very small. So we say since our p-value equals 0.0027 is less than 0.05, which is our alpha, so p is low, so we reject the HO that the mean difference equals 0. In other words, we have significant evidence basically for the alternative hypothesis that the true mean difference in depression scores is higher for placebo than for caffeine pills. All right, so it looks like the caffeine pills are doing good according to this information. They're helping to lower the depression from these people that are suffering from caffeine withdrawals. All right, next thing. So we need to be able to tell when is it a two-sampled mean and when is it paired mean. So when is it going to be M1 minus M2 and when is it going to be mean difference? So here's two scenarios, one for each, I believe. So before exiting the water, scuba divers remove their fins. A maker of scuba equipment advertises a new style of fins that is supposed to be faster to remove. A consumer advocacy group suspects that the time to remove the new fins may be no different than the time required to remove the old fins on average. 20 scuba divers are recruited to test the new fins. Each diver flips a coin to determine if they wear the new fin on the left foot and the old fin on the right foot, or vice versa. The time to remove each fin is recorded. All right, so now, is this paired or is this two samples? Well, we had 20 scuba divers, and then each one was wearing one new fin and one old fin. All right, so each person is doing two things. All right, so that means it's paired. So that is a matched pair experiment when each person does two things. So that means we are working with mean difference. All right, so we just had this one sample. And they did two things. All right, if we look at the other one here, so to study the health of aquatic life, scientists gathered a random sample of 60 piranha fish from a tributary of the Amazon River for 1 year. The average length of these fish was compared to a random sample of 60 piranha from the same tributary a decade ago. All right, so we have one sample, two samples. Two samples from different years and different fish, likely different fish. So this is not paired. So we're not like checking the same fish twice as far as we know. It's not paired. So this would be M1 minus M2, and we would be doing the two sample t-test for M1 minus M2, and this would be the paired t-test for mean difference. All right, so hopefully we can read through a problem and say, hey, well, there's two samples. That means it's going to be M1 minus M2. Or, hey, it's just one sample. That means it's going to be paired data. And here's a picture of a puppy. Thought you could use that. All right, one more here. So now here we have a multiple choice question. All right, we see two lists. Maybe it's paired, maybe it's not. Let's see. Researchers wanted to test whether nitrogen-filled tires would maintain pressure better than normal air-filled tires, which is like 70% nitrogen, 80% nitrogen. They obtained two tires from each of several brands and then randomly assigned one tire in each pair, oh, there's the key word there, to be filled with air and the other to be filled with nitrogen. Chemical symbol for nitrogen is N. All tires were inflated to the same pressure and placed outside for 1 year. At the end of the year, the pressure in each tire was measured. The pressure loss in pounds per square inches, or PSI, and each brand is shown in the table. So this is pressure loss, how much it's gone down. Do the data give convincing evidence at the alpha equals 0.05 significance level that the air-filled tires lose more pressure than the nitrogen tires? So here's air, here's nitrogen, and we're doing pairs. Like this was brand A maybe, and this is brand B, and this is brand C. So these two numbers go together, these two go together, those two go together, and so on. All right, so this is definitely mean difference. Our null hypothesis would be that the mean difference is 0. Our alternative would be that the mean difference is lose more pressure. So it'd be greater than 0. And it looks like we're going to do air minus nitrogen because it looks like the air numbers are, for the most part, larger than nitrogen. All right, so I'm just writing these things down so I know. So if I put this in, say, L1 and L2, or actually L4 and L5, I think is where I ended up putting them because that's what was open on my calculator. So let's check it out on... Sometimes it just doesn't want to turn on. There we go. Stat, edit, and let's see where they are. So there they are. There's the 7.6. That's air. 7.2, that's nitrogen. And the airs are bigger, so we want to do L4 minus L5. And there's our difference. And look at that. Most of them are positive. If most of them are negative, maybe we want to do the subtraction the other way around. But that's what we want to use. So I've got my numbers now in L6. So L6 is the difference. So that's what I want to do my t-test on. So I'm going to do a t-test with data in L6. So stat, test, t-test number 2. Because now we really only have one sample. We're using data. The mean difference we say is 0, so that's our null hypothesis. Our list now is L6. And we want to know, is that difference greater than 0? So that's already chosen. Calculate. And we get, oh boy, we've got a -4 at the end there. So T was 4.5. That's a long ways away. A long ways away from the mean. That's like 4.5 standard deviations away, or 4.5 standard errors away. And our p-value, it had a scientific notation at the end, but it was 7.38, or that 8 would round up, 7.39 times 10 to the -4th. So that means we'd move this up 1, 2, 3, 4 spots. So that'd be 0.000739, which is definitely less than 0.05. So we are going to reject the null hypothesis. We have evidence for the alternative hypothesis. So do we have evidence is what the question was. Do we have convincing evidence? So the answer would be yes, we do have convincing evidence. And here's our p-value that we got. Yep, so there's our answer. And this is the end of 9.3. Yay, we made it through 9. So check out the homework online and turn in your notes. And we got a test coming up, guys, on all this hypothesis testing confidence intervals.